couple of quick announcements. So the first round of PSETs is going to be circulated later this week. One. Information 2 is Wednesday.
Next Wednesday.
We're going to be there.
There's a conflict.
Just keep it in mind. Let's occupy this room and then we kick everybody. The other thing I wanted to say is that in case you have not, if you're not there for the math camp, and if you're struggling a bit with the function analysis that we introduced so far, just remember that there are slides, there are notes, and there's office hours that you can use to catch up. Okay? If you don't know what the L2 and L1 are, or if you don't know what the Hilbert space is, and so on and so forth, either you hang on a little bit more, and then you see how much we actually use this kind of notions. You're going to see it in 1-2 lecture. This is the last one. This is the last lecture, which is full-on functional spaces. Or if you want to fill in some gap, you can exploit the office hours and come around, ask questions to me, George, and all the others. Okay. All right. So as I said, today is the second part of a 2-part lectures on functional spaces. The whole idea here is that for the majority of this course, we're going to be concerned with the problem of learning a function, usually a function with the output that are just real numbers, or even maybe just 2 real numbers, say 0 and 1, given some input and outputs. Okay, so we discussed quite at length a formal way to describe this, and what we want to do now is worry a bit about the fact that if we have to look for functions, we better be able to set up functional spaces that we can use. Okay, not only to give a good statistical procedure, but also good computational procedures. And that's kind of what we did for an hour and a half last week. We began talking about so-called reproducing kernel Hilbert spaces. Okay, we actually started with the spaces of linear functions, just lines, and then linear combination of function that we call atoms or features. Okay, the name atoms come from signal. Probably feature is more like an intuition of what a potential interpretation of these functions. Anyway, we consider these 2 basic examples, and they actually were quite rich. They give us first ideas what we should think about when we think of a good function space. You remember some of the property we asked for a function space? We like function spaces that are made of, we put structure on them. They're not just things, right? So for example, we like when we can add functions, multiply by numbers. We like to talk about orthogonality. We like to take in our product. We like to talk about norms, distances, because there's a lot of tools that we can use to do stuff, okay? And whenever you can talk about the example we made at the beginning, linear function spaces are nice because to some extent, either in linear functions or functions that are a linear combination of atoms, the nice thing is that it's true that we are dealing with functions, but from all practical purposes or computational purposes, we can think of functions as vectors. Okay, vector is just a list of numbers that we have to take to do the linear combinations. The main shortcoming of those models is actually that they're finite dimensional. We can pick many combinations, but the moment we fix the number of combinations, it's done once and for all. So if you start to have more data, you have to change the space by hand. And so the push here is to consider actually, we're going to actually achieve 2 goals. The first one is that we're going to be able to handle infinite dimensional spaces. The second is that we're actually going to learn of different ways to build function spaces. For now, we basically have 1. Linear functions or linear combination of basic functions that we call the dictionary of functions. We're going to learn about more ways to build functions. Far so good? Any questions about this stuff? Okay, so what we did last time is to actually start the brutal way with the most abstract definition of this function space that we are going to introduce, the reproducing kernel Hilbert spaces, which I remind you here. The first thing that you say, okay, I want to go infinite dimensional, and we discovered in the math camp that the way to go infinite dimensional if you have vector spaces in mind to consider so-called Hilbert spaces. Hilbert spaces are essentially infinite dimensional vector spaces. Okay, so you have an inner product structure, you have a norm, you have a distance, and so on and so forth. We actually discovered that we need a bit to assume a bit more, which is basically this property of continuous evaluation functionals. Evaluation functionals are maps that, given a function, evaluate the function at the point. So given a x in the input space, this evaluation function that takes the function and returns the function at that point. And the fact that this is continuous is reminded you here. It's just the definition of continuity for these specific guys. So you fix an x, which means that you fix one of the evaluation functional. And I'm writing also because I switched order last time. I got confused 1 minute before entering class. So you fix this guy. So this is one evaluation functional because you're fixing 1 point. And then you basically say that fix an epsilon, there must be a delta such that if you now take two functions that are close, it means that their evaluation functions are close too. Okay? This definition here is not very intuitive, it's not very constructive. It should show you somewhat. We start from here to see that this is a pretty general thing. Okay? You just have two basic properties. We actually made immediately examples so to appreciate that this is not not everything is a reproducing Kernel-Hilbert space. I often claim that almost everything useful is a reproducing Kernel-Hilbert space because it's such a basic set of properties. But we immediately make sure that there are examples that are not reproducing Kernel-Hilbert space. You remember what they were? L2, the two first function spaces that you probably have learned anywhere. The L2, which is a Hilbert space, but is not doesn't have nice evaluation functional because basically you're looking at the integral, and so you can do whatever you want at a single point. And then there is the other guy, the one which is kind of has complementary properties. The space of continuous functions. Why? Because the space of continuous function, you can clearly check that if you just use the sup norm, the uniform norm, then evaluation functional. So if you put here the uniform norm, evaluation functions are continuous, but it's not a Hilbert space. It is a linear space. You can add continuous function, okay. You actually have a norm, but it does not come from an inner product. So these two examples are not to our liking, and actually kind of what we want to do is to mix these two properties in one. So you appreciate the fact that two functions are close in a norm doesn't mean that they're close at every point. It's a bit of a subtle of a point, but it's going to be important for us. So we already know that there are examples of things that do not satisfy this. We took a step further last time to make examples of things that actually do satisfy this. But before doing it, we actually start to appreciate the fact that this second condition buys more interpretable structure on this space. This one is a bit abstract, but we introduced the other time the notion of a reproducing kernel of a Hilbert space. Okay, so we do assume that you do have a Hilbert space of functions. Okay, so we have a space of function with an inner product, linear structure, and so forth. And we say that this Hilbert space has a kernel, a reproducing kernel, if there is a special function of two variables, x cross x into R with two properties. If I fix one of the two entries, so this becomes a function of one variable, okay, because I fixed one of the two entries, this function of one variable should live in the space. Okay, and today we're often going to use this short hand notation. K undescript x is going to be this function here, the kernel function where I fix one of the two entries. Okay. This is property 1, and property 2 is that if I take any function in this Hilbert space I started from, and now I multiply with this function, I actually get the function at the point. This is what is called the reproducing property of the reproducing kernel. Okay. Notice that up to now, this name reproducing kernel Hilbert space, doesn't really have a reason if you look at any of the terms we introduced so far. The reason why this carries this name, because this is a fundamental object naturally associated to this space. So, and we discussed this a bit, is that we basically have this implication, okay? If H is a reproducing kernel Hilbert space, then it has a unique reproducing kernel, okay? So if you start, yes? That guy? That's the definition. So the question is whether that function has to be symmetric, okay? And according to my definition, that's all you request. Symmetry is gonna be a byproduct of that, essentially, okay? You'll see in a minute that, and you almost check it with your eyes, that if I assume those two properties, symmetry is for free, and it comes from the inner product. We're actually gonna see that not only you have symmetry, but you have even more, just out of that. So introduce this definition, we introduce the definition, and then we discovered last time that they're intimately related, because whenever you make this assumption, it turns out that you have one of those functions for free, and in fact, only one, okay? And the proof of this we skipped, because it's basically based on a dimensional analysis result called the Ritz lemma, or Ritz representation lemma, and is one line, but it's all hidden in a deep result that is kind of hard to appreciate and is not very constructive. So I want to skip it today too, but I'm happy to discuss it offline. We actually looked a bit at the opposite connection, which is if I give you a space, a Hilbert space with a special function, a reproducing kernel, what happens is that then that space is a reproducing kernel Hilbert space. Okay? So if I give you, if I assume that there I have a space H with this special function, then it is a reproducing kernel Hilbert space. So if K, like this, K reproducing kernel of H, then H is a RKHS. The proof of this second statement is actually elementary, and that's what we showed. Okay, basically, once you assume that you have a reproducing kernel, essentially this gives you evaluation function. So this one definition here, you can check that they are continuous. Ritz. I have a 50% chance of misspelling it, but I recently checked, so it should be correct. That was it? All right. Yeah. It doesn't have to. It is. It's effective. I mean, it is. Here you start from one. You start from one, and you discover that the space is a reproducing kernel Hilbert space. So there's no space. Wait a minute. So we have to stick to definition now. A reproducing kernel Hilbert space right now is this definition here. There is no reproducing kernel inside. Okay. Then I do define a reproducing kernel. And then I discover that if I make this assumption, I have one of those functions, only one. So there exists one, and it's only one for free. So in a sense, there is, once you assume there is a reproducing kernel Hilbert space, there is always a unique reproducing kernel associated to it. Okay? And in fact, we actually gave a new definition given this. Basically, we just said definition 2 of RKHS, which is equivalent. So this is the definition 1, if you want. Definition 2 is I keep assumption 1. Okay, assumption 1 is the same, but assumption 2 is it has a reproducing kernel. Okay? These are the two, just putting together these two facts. I can trade the assumption of continuous evaluation function with the existence of a reproducing kernel. It's all the same. Okay? So this is basically the main content of the stuff. There is a bunch of stuff to digest here, okay? But I'm just trying to put some order. What are the implications? And you often have to, today, you often have to remember what you know and what you don't know, in the sense, what you define. So what are the assumptions and what are the consequences? For example, in this definition, there are not reproducing kernels, okay? There I introduced the reproducing kernel, and then here I made the connection. So I assume I have no reproducing kernel, and then I find out that I have one. So here I assume that I have no RKHS, but I have a reproducing kernel, and then I found out that I have one. Okay, so you have always to remember what you have and what you don't have. Today, we're going to see that there are tons of implications of different objects and things that are equivalent, so we often have to do a bit of a imagination effort to remember what we are assuming and what we're trying to do, because we're going to have 15 things that are all equivalent to each other. So you often have to remember that. Yeah.
It's well defined, but is there can you give some sort of intuition about what reproducing kernel is or gives you in the space? I understand the definition, but I'm just looking for a little more intuition.
So we're gonna show mounting evidence in this trial to reproducing Hilbert spaces that this guy has extra structure that is kind of interesting. Okay, so we're gonna build many intuition of the. We're just gonna see that basically this second property here is gonna give stuff for free. Okay, so one first observation is the fact that this second condition is not. It does already give you some structure, because if you take L2, then it's not true if the two functions are closed in L2 norm, they're closed pointwise. Okay, so this gives the first hint that is constraining not to all possible functions, but already to some potentially large, but still a nicer set. Okay, so there's a first. Then you find out that you have one special function. But again, it's not obvious. And what you see is that you have an operation and in some sense linearize evaluating function, because evaluating a function becomes an inner product. If you think that's kind of what happened when you have linear functions, right? You have that when you want to evaluate a function, you have to take an x and multiply by a w. And then you get a linear operation. This is doing something like that. Okay? So it's a bit abstract, but it kind of starts to give you, again, some more intuition maybe. Okay, still mathematical. Then we keep on going. And one way to keep on going and try to get a better idea is to give examples. Okay, and that's the second thing we did. We're basically running out of time, so we didn't do a long way, but we saw that the main example we saw, that is the case where, so the example one was the case where I give you a space of atoms or features, assuming that these guys are linearly independent. Okay, so these are functions from x to r. And then what I do, let me just use this compact notation, is that I take the span of this phi j. Okay? I take this span just means that I take the linear combination of the phi j. We introduce D and show that we can give a Hilbert space structure into this. Is a nice Hilbert space. It turns out that it is also a reproducing kernel Hilbert space. And this we actually did in details. And we saw that the kernel was simply given by so that in particular, we can consider the case where we just consider the phi j to be the function that extracts the jth component of a vector, and so we get linear functions. So linear functions are a special case of this, where x is equal to rd. We saw that the two examples we made before, linear functions and functions that are a linear combination of finitely many dictionary elements that are linearly independent, that's important. Then both these examples are reproducing kernel Hilbert spaces, and they have a reproducing kernel. Here I'm showing you the reproducing kernel. And we actually proved this. Okay? So if you want, this gives you, by inclusion, start to give you some more intuition. Common things that you usually use are contained in there. So a natural question is to see, okay, what more is in there? Okay? Both these two examples are finite dimensionals. Okay, so we didn't quite pay off going in this level of generality. The other example we introduced is band-limited functions. So we saw that L2 is not okay. So let's actually put the, remember that the Fourier transform, I'm going to be sloppy about normalizations. And just consider the one-dimensional case. And if you remember, when you do something like this, you're taking the Fourier transform of a guy. You can think of this as a one-dimensional signal in space, f of x, and now you take the frequency point of view. So you can view of this as the kind of a frequency description of the same signal. Okay? If you consider a simple case, this just becomes a sum of sine and cosine and so on and so forth. The space of the space of band-limited function is a subset. For technical reason, you have to take not only L2 but also L1 for this thing to be well defined. Let's not indulge in that too much. Let's just say that I'm going to consider functions such that if you take f of omega, this is different from 0 only when omega is in minus gamma gamma. Okay, where gamma is some positive number. This means that if I go look at the frequency context, so if this is omega, and this is my omega, stuff can happen, but then it disappears. Okay? There is a minus gamma after y. There is no content in frequency in the frequency domain. What does it mean? If you look at this as the description where larger value of omega are associated to higher frequencies, that's the classical, Fourier analysis description of a signal, then it means that I don't have high frequencies. Frequencies at their critical value are not present. They're not there. Okay? So this is clearly a smaller space than the whole L2. I'm actually going to consider the inner product in H to be just the usual inner product in L2. Take any two function in H, they're also in L2, and I'm just going to consider this to be the inner product. Okay? Clearly, this is less than the whole space. The question is if it is a reproducing kernel Hilbert space. And it turns out that it is. The kernel, given by the sign of gamma x minus x prime, gamma of x minus x prime. When I say x prime, I mean x bar. Okay? So this is a claim, okay? And it needs a proof. I'm going to do the proof in details, but let me just start it. You remember that if this is I'm going to tell you what is important in this story for a minute. Let me finish to sketch the whole story first. This is the Fourier transform, and you remember that there is an inverse Fourier transform that given f of omega, integrate now over d omega, and here you have to put the plus, then you get back f of x. Okay? These are the two basic equations. Again, I should put a proportional there. There are constants, and I'm just being sloppy about it. How do you prove that this is the kernel associated to this, so that this is actually a reproducing kernel? How do you prove that this is a reproducing kernel? We basically want to prove that we're going to use this definition. We're going to use this property. We use the fact that it is a reproducing kernel Hilbert space if I have a reproducing kernel. And we basically have to check these two conditions. Okay? So how do you do it? Essentially, you start from here. Step one is that this is a good point, right? You have f of x equals something. You want now to show that it's an inner product of something with something else according to this inner product. So what do? Well, you just remember that this f of omega doesn't live everywhere, right? They live here, right? So this integral is actually not over the real line. It's just between minus omega and omega. So I can actually write it as omega x. Then you have to put the indicator function of the set omega, right? And then basically you're done. Once you've done this, you just have to say, okay, but now I just want to use the partial identity for the inner product. Remember that the inner product in space and frequency are related. So you have to, this is the function you want to take the inner product with. And then you just have to take the inverse Fourier transform of this guy. And it turns out that if you put, the second example of function of which you want to compute the Fourier transform is exactly the indicator function of an interval in the real line. And it is actually given by the sink. Okay, and this is just the sink. So that's it. So you write this line. You just have to complete this by remembering what is the Fourier transform of this guy. And then it's finished. So this shows an example. I'm skipping a bit because this is an exercise, okay? And you can do it offline. Our main goal here is not to remind you what is the Fourier transform. If you know it well, if you don't know it, you can decide how much time you want to spend on it. But you can appreciate two things. Once we're actually dealing with the infinite dimensional space. This space is really infinite dimensional. It's a space of all possible functional L2 with bounded support, okay? Can I describe it with a final set of parameters? No, okay? We're really dealing with a big space now. Is it a ginormous, insane space? No, it's still a subset of L2 where the frequency content goes away after a while. And it's the first example of so-called translation invariant kernels. Because if you see, the kernel doesn't depend on actually x and x prime separately, but only on their difference between these two guys. Okay? Okay, so it is, if you want, start to be another little piece of the puzzle. If I consider this special case, now I have function spaces that have some structure, because if I take a Fourier point of view, this is just an example, I don't have arbitrary frequency content, but only some kind of restricted frequency content. Now this is actually interesting, because now you can say, one question you can ask is how much you can generalize this. Okay, and it turns out that there is a whole family of reproducing kernel Hilbert spaces that are example obtained just by relaxing this assumption. How? How can we relax this example? Here we are assuming that if you go in frequency, there's stuff happening and then nothing. Okay? And we already know that if we don't make any assumption, we just say stuff can happen wherever, that's not an example. That's just L2, and it's not an example. What is something in between? The question makes sense? So he's saying, well, I want to make this guy large. Okay, but it's this case, okay? So the intuition is in the right direction, but strictly speaking, I can let gamma be whatever I want. I just don't, if I let it go to infinity at some point, it's big. But for any finite gamma, so I guess I should say that it's bigger than 0, but smaller than infinity, okay? Then I'm fine. But the intuition is correct. I would like to start to put stuff in there. How? Well, yeah. You decide how much stuff you want to put outside, so to say, intuitively. Okay, you have to basically just say, okay, my function is not going to be 0, but it's going to have some kind of decay. Okay, you're going to decide what is the shape you allow to have outside of this interval, roughly speaking. So, for example, you can ask, I want to have functions that when you look in Fourier, they have an exponential decay. Okay, what exponential? Can you do polynomial? Sure. Instead of having super fast decay, you have a gentler decay. Okay. What are these spaces? Do they have a nice structure? Are they reproducing kernel Hilbert space or not? Okay. And it turns out the answer is yes. Consider again. You consider the general case in the interest of time. So consider that same, consider now an H, which is the set of function in L2R cross L1R, so it's the same stuff as before. And I make this function so that if I now take f of omega, it's not 0 somewhere, but if I multiply with an exponential, I gotta get 0. I want to make. What does this say? This says, you see, I'm multiplying by a function which is increasing exponentially. This is a big sum, okay? I have a sum of two terms, of the product of two terms. One is increasing exponentially, so when omega becomes big, these things explode. And I would like this sum to be finite. It means that this has to do what? Counterbalance this effect. It has to decay. How fast? Is it polynomial enough? No, because this is exploding exponentially fast. This guy should go down exponentially fast. So I'm basically saying, see this picture? I'm allowing myself to actually get out of here as long as I have a fast exponential decay to 0. Okay? And I can still, if you want, put a gamma here. Okay? Or there is some kind of telling you how fast as an exponential it goes down. It tells you how the shape of the tails. Yes? So, because I want an exponent, well, I don't want an exponential. I'm considering now, right now, I'm considering a Gaussian decay. Okay? It was exponential we use in generic terms. Okay. So if it is in that, so how are these two spaces related so far? Well, who's containing whom? Is this guy larger or smaller than that? Is larger, right? Of course, if I'm there, this is true because there's nothing after a while. But if I'm here, that's not clear. Correct? So that space is strictly containing to this. I'm considering a larger space. It turns out that it's not okay to consider that the inner product is just in L2. I have to reweight it somehow. So the inner product I have to consider is actually something that looks like this. Before, I was just doing the one in L2. Oh, there's too much stuff. So I have to take some kind of weighted inner product in L2. It's not okay to just take the product in L2. Yes. Yeah, and I think it should not be there. Yeah, this is just a type. Okay. So what I'm saying is that this is the right inner product from this space. This is not so surprising because you see here I put L2, but you could actually write it in the frequency domain, and then all these functions are only comparing between minus omega, omega. Here I'm basically doing a similar effect, and I'm just considering, in some sense, a weighted version of this inner product. Okay? Again, what is the take-home message here? Relax that assumption, consider an appropriate inner product turns out to be the right choice, and then what you're doing, you're building a reproducing kernel Hilbert space. What is the kernel? The kernel is just the Gaussian. Constant and dependent gamma. Okay? I just consider one dimension. I'm considering this idea that I have function that have a fast decay in the Fourier domain. And then it turns out that these functions are exactly reproducing kernel Hilbert space where the kernel is the Gaussian. Okay? Okay, fair enough. Can I keep on going? Yes, we'll just make one last example, and then we stop it here. The last example is going to be similar. So it turns out, let me say, it turns out that, well, no, whatever. Let me give the last example first. The last example is, again, very similar. I'm basically going to replace so I take again L2. And you see, basically, when I pick that shape, I'm taking here the shape of how fast I have to be, right? I'm going to consider another shaping function. And this is going to be one plus omega squared d omega. Okay? Not just anything, but this one specific shape. Again, the inner product is going to be same idea as there. You see that there is this function popping out to reweight the inner product. Here, the inner product is going to be reweighted now by this. Prime h is going to be f hat omega, f prime hat omega, 1 plus omega squared d omega. Now, again, this can be shown to be the kernel xx prime, which is just the exponential. Oh, sorry. Or some appropriate constant here again. So similar, so let's see what we did. We basically, instead of assuming a fast exponential decay to 0, let's assume just a polynomial decay, the basic polynomial, which is squared. Okay? Then it turns out we don't get the exponential. So we don't get the Gaussian. Okay? We actually just get an exponential. So a distribution which also decays much with tails that are much more fat. It's much slower decay. Okay? Thanks. Okay? Yep.
And say that it's a reproducing kernel.
That's a bit what you're doing, right? So he's asking why don't you just go all the way to the limit, or basically taking this guy to be infinitely peaked and so on. Essentially, we want to do that in a way that is more controllable. You know that you have to go to delta function, you have to deal with distributions and everything. This is kind of like generalizing that idea to much broader classes, okay? So that would be the case where we allow, to some extent, to take the whole L2, and in fact, then everything, it doesn't really make sense to talk about evaluating function at points, and then you have to consider a weak sense, a distributional sense, so if you have to be precise. So we're trying to do the same thing without the headache of having to work on the whole thing. So we actually restrict the space, instead of working on the big space and weakening my definition of what does it mean to evaluate functions, I actually consider a regular definition, and I consider slightly smaller spaces. And notice that this gives me not one space, but them. Okay, at some point, we're going to consider a case where, suppose that a minute ago I would tell you, oh, try to use one of these spaces. They will look like all different examples. It turns out that they're all just different kernels for us, okay? And we can all describe in a unifying picture. What is interesting in this story, that result is another way to answer his question. Okay, what are these guys? What are these complicated abstract guys? Well, okay, you know, there is the first 3 lines of Fourier analysis to remember, the definition of the Fourier transform, the inverse, and the first 3 examples that you find, the indicator function, the Gaussian, and then that guy, 1 omega square. And then these are all examples of reproducing kernel-based space in the special case where the input space is R, okay? And it tells you that these are spaces that somewhat have some kind of regularity in some precise sense. In which sense, if you think in terms of frequency, not all frequencies are allowed. So high frequencies should go away. How fast they should go away tells you in which space you're living, okay? Far so good? So in some sense, this is an infinite dimensional space of functions that are simpler than this infinite dimensional space of function, which are themselves simpler than this other infinite dimensional space of function. In which sense that if you look in the Fourier domain, there is you allow more and more stuff to happen, yet not the whole L2. Okay? Far so good? So one way to generalize this is to actually say, look, can I play? You see, this last 2 examples suggest perhaps a way to go beyond these 2 examples by basically saying, can I just, there seems to be some nice function that I'm using. I use it twice. I use it to say how fast this has to go to 0, and then I use it to reshape the inner product. But then, boom, I got some kernel out, which is related to the Fourier transform of this thing here. Here the same. Use this one function here. To reshape it. Can I actually consider some generic, and it's a function of one variable, okay? So can I just consider some function of one variable, kx, and use its Fourier transform to build spaces of function of kernels, just by telling you exactly what kind of shape you have? Yes, you have. And what do they have in common? All these kernels are all going to be of the form k. So kxx prime is going to be kappa of x minus x prime. They are translation invariant, okay? So one of the biggest class of spaces that is used in for example, in signal processing all the time are translation invariant kernels that are these kind of guys, okay? And all of them, again, you start from a function kappa, okay, not our k, just this one-dimensional function kappa. You take its Fourier transform, you do what you have to do, and then if you want to back to the kernel, you have to take. So again, this is maybe this is too similar. Okay, so this is my k, the usual k, and this is a function kappa of one variable, not of 2 variables. And I basically consider its Fourier transform. What are the properties of the Fourier transform? It has to be positive. The Fourier transform has to be positive, essentially. Let's put it there, okay? Kernels equal kappa of x minus x prime, because this is a function of 2 variables. That's of 1, so I have to do something to make them equal, right? So it's true for all the example we made. Okay? All right. So this is one possible directions. And there is a ton of material on this kind of stuff because this kernel is very important. And you can, essentially, you can generalize. You see, I consider always the input space, x, to be R in all this. Clearly, you can consider, instead of R, RD. But then, whenever you can define a Fourier transform, you can try to use these results. Okay? So there are many situations where you can define Fourier transform for more complicated domains. For example, some of you might remember the Fourier transform is related to the group of translation, so you can consider other spaces and groups and define much more general notion of Fourier transform on grids, on Z, on graphs, and so on and so forth. Okay, so this is one entry point, which we're not going to discuss, for many classes of kernel on a more exotic domain than R. And basically, the entry point is the Fourier transform. Okay, so that's why we spent half an hour discussing that. Fourier transform is going to disappear from our life right now. Is there any question you want to ask before we depart from it?
Where do you get the kappa? How do you get it?
The one that is needed? Well, how do you get this guy? How do you, why did you choose it? And how do you get this? Okay, so I'm not telling you how to pick kappa, or I'm just telling you, I'm giving a name to something that we've been using, so that instead of 2 examples, you can build as many as you want. Okay? And this is related to a result so-called Bochner theorem. Is one way to check if you're dealing with nice reproducing Hilbert spaces. Okay, anyway, other questions on this? All right, I like that question. Before we actually we depart from this story, we spend a bit of time because this is a big example, okay? Is it the whole thing? No, it's just one example, okay? We made the example of linear functions, and this is just another example. Before we depart, let me just show you another way to look at this same space. Turns out that you actually, if you do a bit of calculation, you can check that the norm in H. Again, you just have to remember that, look at, this is the norm of the function, okay? This is the norm in H. And you see, I basically get f omega square multiplied by 1. Now, if you go back in the space domain, this is what? This is just the L2 norm of the function in L2. Okay? This multiplied by 1 is just it. Okay, and I know this is not enough because this is not a reproducing Hilbert plane. In fact, I added a little bit more. I added the norm. I added the integral of f omega squared times omega squared. Okay, what is it? Remember? Anybody remembers the second line of Wikipedia entry of derivative, right? So this is the Fourier transform of the square of the derivative. So basically, this is plus not f in L2 because I already had it, but f prime. Okay? This gives me another way to think about this guy, and in another possible direction of extending this whole example. Forget about frequency, we hate Fourier transform. Well, this is one way to start the story. What does he say? He says, look, fair enough, I'm going to look at how much surface is under my curve, and then I'm going to check the average size of the gradient or the derivative in one dimension. What does it mean? Take the derivative, and then you just see how it varies at every point, and then you sum it up. Okay? So if you have something that is like this, or something that is like this term is going to be very, very different. Okay? This function has derivative which is essentially 0 everywhere. This function has derivative that changes all the time. And so when you integrate, the value of the derivative at every point is going to be huge. This, if you want, is a time perspective. If you look at what my hands are doing, they're just doing this all the time, right? So I call it frequency in one case. I call it change derivative in the other case. It's the same story. For one, you don't have to talk about Fourier analysis, and you just think of changes of derivative. For the other one, you think about in terms of Fourier. But it's the same story. And you can see that now you could basically say, why did I take the first derivative? Can I consider the second derivative? Okay? Yeah, and what's going to happen? You're going to consider different powers here. So if we started this way, we'd end up in the same direction, basically saying if I with a square, then I consider to put, and this is the minimum amount, okay? Then you take second derivative, you're asking for more, third derivative for more. And then I say, oh, but this is all polynomials. Can I consider exponential? Yes. And what about just something that is zero outside? Yes. So we went just the way around. Okay, we started from simple, we got from complicated. Here we could have started from this with somewhat one of the most complicated cases and keep on going down. Notice that this one example here, where I just take the first derivative, is special for the one-dimensional case for x equal to r. there is a whole story about embedded theorems and so on if one considers RD. But again, this is a small remark for those of you that are interested about it. Fair enough. So let's stop 1 second. This was kind of a long example because it's an instructive one. But let's see where we are. Okay? Use this big function space that they are. We start to understand there is some structure in them. We start to look at examples. And then we enlarge with a big class of examples. They start to have a lot of stuff inside because most of the stuff that you've seen probably in signal processing is already in there. Okay? Or at least the more elementary stuff. So what is there more to say? Well, it turns out that there are many more stories to say, and we actually could have started from another perspective, which is perhaps the more popular one. So let me mark before I delete everything. Notice that we actually achieve two things. We describe function spaces that we can build in some reasonable way. And we also notice that we actually, the norm in the space has a meaning. A function with a big norm is a complicated function. A small norm is a simple function, in which sense that one wiggles a lot and one doesn't wiggle much. Okay? So we actually achieved two goals. We have building big infinite dimensional space, and we're using a testing thing to just check who's complicated and who's not. And this testing thing, which we're going to call a regularizer in a class, is going to be the norm in the space. Okay? Okay, so what there's more to say? One of the beauty and complication of reproducing kernel Hilbert spaces, and one of the reasons we actually spent 2 classes on them, is that they have that one single second property buys you much more stuff. Okay? And this much more stuff is sometimes confusing to put in order because everything turns out that there are many equivalent properties. So let me do a little diagram. So what did we introduce so far? We introduced the notion of reproducing kernel Hilbert space, and if you want, the notion of K, it's a reproducing kernel. And we use the equivalence essentially between these two things to go back and forth. Okay? Now, suppose I give you, it turns out that if K is what is called a positive definite function, which I'll describe in a minute, it turns out that I actually can build, if I have a positive definite function, if I start from this, I get one positive definite function for free. And if I actually start, I don't have any of that. Okay, I just have a positive definite function. I can build a reproducing kernel Hilbert space. So for legitimate purposes, you could have started from here because they're equivalent. It turns out that they're completely equivalent. I can start by saying, you give me a positive definite function. Let me show you all the beautiful things you can do with it. Okay? Suppose that instead, you come up with the map from the input space to some space, okay, of descriptors. You can think of it as a list of numbers, but it can actually be infinite dimensional. It doesn't have to be vectors, doesn't have to be functions. It's stuff. What kind of stuff? It is a Hilbert space. So you do have an inner product. It's a legitimate infinite dimensional space. Okay? Again, the game here is whenever I introduce a guy, nothing else exists on the board. Okay? Now there is this guy and nothing else. There is the input space. I came up with the space F, and now I map my input point into the space F. Turns out that whenever you have one of these guys, you can define one of these guys. Which means that you can define a reproducing kernel Hilbert space. So if whenever you can come up with anything like this, you're actually building implicitly a positive definite function and a reproducing kernel Hilbert space. The other way around. Once you have a reproducing kernel, which is actually equivalent of this, immediately you have this map, and in fact many of them, for free. Okay? More than that, rather than building the space by first building a positive definite function, you can actually build it directly. And this is going to give you yet another point of view. Okay? Don't stare at this too much. We're going to discuss this. I'm going to try to at least sketch some of this connection in a minute. But all the point I'm trying to make right now is that besides the object we introduced, there are actually two other concepts, positive definiteness and feature maps. They are well-defined objects, and they're completely equivalent to what they describe. Okay? And the thing is that, there are a lot of, you see, 1, 5, 6 possible directions to discover. And every time you do this game, the hard part is to remember what you assumed. Because if you assume you have a feature map, you cannot assume you have a reproducing kernel space already. Otherwise, it's going to be, tautology and keep on going. So the reason why we describe this is because this is going to provide us 3 ways, not one ways. Okay? We already have one way. We're going to have more ways to build function spaces, and they are to some extent equivalent. And as in this case, some of the direction actually require complicated math, but some of them are actually not that complicated. Okay? So what we would like, there is one extra guy in the picture, which is the so-called integral operator associated to the kernel. This is probably the most complicated of this story, and yet it was one of the most popular a while ago. It's basically a big kernel matrix, for those of you who knows what's a kernel. Otherwise, if you don't know what's an integral operator, that's it. And it turns out that also you can start from here, and you don't get quite an equivalence, but you can build feature maps or kernel or reproducing kernel out of this object. Okay? So the thing is further complicated. We have 1, 2, 3, plus 1. Okay? And basically, again, post-def function is what is attached here. What is attached here is the notion of feature map. And this is typically what is lagging behind the notion of Mercer theorem, okay? Which again is a very basic result. It's called the Kalun-Leuven expansion in Gauss. Okay, so let's, we don't have a lot of time, so we're probably going to finish a little bit next class, but I will try to keep it small. So let's start to investigate this direction a little bit, okay? So I show you that once you have a reproducing Hilbert space, you have one special function for free. We're going to discover that this special function is even more special than we, okay? It's so special that I could have started from there and build the Hilbert space from scratch. So we first need to define what we mean by positive definite function, okay? So again, I'm going to try to emphasize this, but if you get lost, let me know. Every once in a while, we're assuming that there is nothing, and there is only the one thing that we are discussing right now. Right now, we're assuming that there is no reproducing kernel space, no reproducing kernel. There is only this function I'm defining now. Okay? So X is a set, and K, there is no Hilbert space inside. There is nothing. Okay? There is one function of 2 variables. So it doesn't even make sense to even think about those properties, okay? Because I don't have the object to define those properties. It's just one function, and it has the following property. Take x1, xm in x, any, no training set. There is not even a probability distribution on x. Just take any sequence and build the matrix, okay? Entry are given by kxi, kxj. So ij from 1 to m. Okay? I say that this function is positive definite if this matrix is positive semi-definite. Okay? What does it mean? That if I actually go in and diagonalize this function, it turns out that the eigenvalue can be positive or 0, but they cannot be negative. Okay? It's an assumption. Not all possible functions are going to have this property. I call a function positive definite if it has this property. Okay? This is one easy way to remember, because I'm basically saying, okay, I build the matrices, and I know that these are nice matrices in the sense that they don't have negative eigenvalues. Okay? We're not going to discuss it. This is a standard fact that, saying that a matrix has positive or 0 eigenvalue is equivalent to looking at the quadratic form of the matrix, right? So it means that if you take this k bar and you multiply by some vector, then this has to be bigger or equal than 0. This is the same thing. So alpha here is a vector in Rm, and this is a product in Rm. This is another way to say positive semi-definite. Agree? So let me write this down using the kernel function, okay? If you expand the product, you get the following thing. Sum over I and j of alpha I, alpha j, k, xi, xj. Okay? This again is another way of writing always the same condition. Agree? I just wrote the inner product explicitly. Okay, before we actually try to figure out the connection with reproducing Hilbert, let's just do a simple exercise. Let's check that the inner product of two vectors, if you take the specific example where x is Rd, the inner product is a positive definite function. So take example, x equal Rd, okay? And take k to be equal to x bar in Rd. I claim it is a positive definite function. How can we show it? Many ways of doing it. I show you the one way which is going to be useful in a minute. Write this last expression and replacing the kernel with this one specific kernel we're considering, which is the inner product. Okay, I use the word kernel, but it's just a function for now. So we're function with this example. Okay, so now I need to check that this sum cannot be negative. How do I do that? Notice that I didn't write it here, but when I write this equivalence, here you can take any sequence. Here you also add the fact that this is any vector in Rm, okay? Okay, so how do I check that this is, do you see how I can check that this sum cannot be negative? What? You have to tell me what you want to do after that because I don't see it. Right, that's one way to see it. If you want, one way to see it is rather than going this way, you can just say, look, if I actually write the matrix K bar, this is another way. You don't go this way, okay? This is another way. This is going to be X transpose, where X is the matrix with row Xn, Xm, okay? I put all the elements one after the other, and I just get this thing. And this is just an inner product matrix, okay? But I'm now relying to the fact that I have to prove that now this is positive definite, and this is very close to a proof, okay? Another equivalent way is to basically say, look, let's check that this is just a norm of a vector, okay? How do you do it? This is linear. Let's just push the sum inside, okay? So there is a sum over I, sum over j from 1 to m. So let's put the sum over I inside. Let's put the sum over j inside. And what do I get? I get a vector times itself. I get sum alpha I xi, sum alpha j xj, Rm. And you see now I call them with different indices, but it doesn't really matter because I can really just give the same name, which means that this is just the norm of alpha I xi, I from 1 to m. Agree? Simple enough? Turns out that this is pretty interesting because the example, first of all, it gives a first example of a class of functions that we know how to check whether they're positive definite or not, okay? Whenever you have something that looks like an inner product, it's positive definite. You could check, for example, if you take the inner product given by a set of linear atoms that are linearly independent, you can just check and you get the same proof. In general, it's not obvious how to check that given a function, whether it is positive definite or not. An interesting exercise you can do is, for example, try to see the case where you want to check that the example we discussed a minute ago, all the translation invariant kernels. If you just start from the translation invariant kernel to prove that it's a positive definite function. And again, it's from idea in the continuous setting. For example, if you can consider, instead of the linear kernel, you could consider, for example, something like this. D, okay. Polynomial function, so you take the inner product and then you take possible monomials over up to D. And you can check that again, this is positive definite, okay? One way to do it is basically checking that it's an inner product again in the monomial space, in the space of all possible monomials. And I think that actually you're gonna do this for, in the P set, and Tom is probably gonna discuss this a bunch of times in a month or two. So we're not going to discuss many examples. We're actually going to use this one example as our primary case. But just remember that in general, noting that a function is not positive definite or not is one of the hard things to do. What we care about is instead start to investigate. So we now know what it is. What is this? Okay? We know what is this because I just defined it. How is it related to what we discussed a minute ago? So first of all, we want to check that if you start, okay, now the game is what we have and what we don't. Suppose that now you know the definitions, okay? But I assume to give you H and its producing kernel. Is it a positive definite function? Yes or no? Does that make sense? I give you H, so you can write down the inner product, it makes sense, you have it. And I give you a reproducing kernel, so it has that property. Is it a positive definite function or not? And my claim is that that proof is all you need. Why? Because look at the trick we did here. So take now X to be any set, and K a reproducing kernel on some space H of functions on X. Now, we want to check that if you do alpha I, alpha j, k xi, xj, this is bigger or equal than 0. And all the thing we have is those two lines. Which one do we use? This one looks nasty and it's probably still nasty. This one actually looks kind of interesting. Because look, it says that I can write k xi xj. How? Well, this is just the function, if you want, it's just a function kxi evaluated in xj. Right? So how can I write this? I want to write it as what? As an inner product, because once I've done that, I'm going to be basically done. So how can I write this as an inner product? Okay, I want to use the second property.
KXI with KXJ.
Exactly. Okay, so all I want to do is to say this guy is just the inner product of, let me write it, kxi dot for k j dot. Okay, I can, everything is legal because this function belongs to this space, and when I multiply them, I actually evaluate the function in the other point. So this is just an identity coming from those two properties. You agree? Okay, so let me rewrite it using the other notation, which is a bit more compact. So I can write this as kxi, kxj. And here, if you want, you start to have yet another manifestation of the kind of nice thing in this. These spaces are more linear than usual linear spaces. More linear structure in a way. Because whenever you do inner product or evaluation, it becomes just an inner product. Okay? So what do you do now? This was just an inner product between two vectors. This is more complicated. It's an inner product between two functions or more complicated object, but who cares?
Take out the second argument, that's still in H. But if you take out the first argument, is it defined to be?
Sorry, because the thing that you can check from this definition, we actually remarked it and I forget, that you can check that from this definition as a consequence, what you have is that kx x prime is symmetric. This essentially comes from the inner product, okay? It's just the inner product is symmetric. It doesn't matter which order you use, and this is exactly what's going on, okay? So I skipped it before. This is just a simple consequent exercise. So I'm using the fact that doesn't really matter. The order doesn't matter, okay? I did it here for what matters. I can just do it like this. The order doesn't matter here, Okay. Okay. So what do you do now? Nothing. You put the sums in, and you're going to get sum alpha j, k, xi, xj, j from 1 to m, square in h. And of course, this cannot be 0 for any generic alpha. It's 0 only if I take O alpha equal to 0, or if I take a crazy kernel, which is always 0. So this one specific example is actually pretty general because it shows me a pretty general thing, which is that any reproducing kernel is positive definite. Right? And you can easily check that it's symmetric too. Okay? So if you want, done. One direction is done. Okay? Good. So what would be nice, now that we know that, you see the game. The game is, oh, when I have this object, I have this other object for free. Can I go the other way around? What would be the other way around? Suppose that I give you a function k with those two properties. Oh, sorry, with that property there. And let's assume that it's also symmetric. Can I build a reproducing kernel Hilbert space? So George tonight goes home and he doesn't sleep and he invents a positive definite function which is symmetric. Can I use it tomorrow as if it was one of the Gaussian or the inner product? Can I use it the same way I use those? Well, what does it mean? Can I build a space from it? How does it look like? You see, in all these cases, the space was given, and then I just look inside and say, okay, what kind of space I'm choosing? Here I'm doing something less. I just take one function, and I want to know if I can build the space. Okay? So I don't have anything but a function with that property. The answer is yes. And the proof is constructive, and it has some parts that are technical and some parts that are instructive. So I'm just going to sketch the proof, and I'm just going to show you because of the part that are interesting. Okay. So before I start to basic idea is essentially, again, now you see the game is now I give you k, build the h. Okay. So given k pos def, build a kernel Hilbert space. Okay, this is what we're after. This is our goal. If you want, it's going to be a theorem. The theorem says every positive definite function defines a unique reproducing kernel Hilbert space. How? Well, I just show you how the proof works, which is going to be a few steps. The first thing you do is that you try to start to build H, okay? But it's going to be complicated, so we're going to build a simpler version of H. What is it? It's a space of all possible finite combination. So these are functions from x to r. It looks like this. Alpha I, kxi, okay? And this is my f. X, alpha 1, alpha m is in the natural numbers. So let's parse this expression a minute. I pick a kernel, and if you want to have something in mind, think of a Gaussian, for example. Okay? I take a Gaussian kernel, e to the minus. If this helps you, just think of this. One example. I take this one function, now I take linear combinations of this function centered where? Anywhere. And what with weights? Anything. And how many? As many as you want. Doesn't matter. Okay? Let's see how we are in building a reproducing kernel Hilbert space. Is this a linear space? So if I take two functions that look like that, do I get a function that look like that? Yes. Maybe I have to, consider, kernels on different points. I'm going to have a larger sum, but whatever, it's fine. Okay? If I multiply by a number, do I get another of those functions? Yes. Do I have an inner product so far? I don't have it. I had to build it. Okay, let's do it. The basic idea is to first define the inner. Remember, to define an inner product that is going to smell like reproducing Hilbert space. How? Suppose that I give you two very special functions in this space. Okay, Ax, and let me just use the short notation. Well, no, let's use that because I used it there. So let's consider this function. Does it belong to the space? Yes. Let's consider this other function. Does it belong to the space? Yes. So this space is called H naught because it's not going to be the whole thing for now. I need to define this. And how do I define it? Okay, this is the definition. I defined the inner product like this. It didn't exist a minute ago. Now it exists. Okay, on these two guys. It's easy to check that now you can define an inner product on any two guys in that space. If I give you, say, a F that looks like this, and now I give you a G that looks like beta J, K X tilde J dot, J from 1 to capital N. Okay, and now I tell you, okay, tell me how much is the inner product between F and G in H0. Well, how much is it going to be? Well, you use essentially linearity, and you write sum over I and j from 1 to m and n, alpha I, beta j, k xi xj. Okay? Any two function, you can build a function space like this. Okay? Sorry, any two function, you can build an inner product just like this. Now, you have to prove that this is an inner product, okay? It's clearly symmetric, so you have to prove that it was all the other product, and we're going to skip this, okay? We're also going to prove, we're going to skip the last step of this proof that every positive definite function gives a reproducing Hilbert space, which basically means that we have to check the story about Cauchy sequences. You have to be sure that everything is there. And that's basically the point where we're basically going to have to complete this space. We have to be sure that every accumulation point of sequences is in there. Even just from what I just said, it's clear that this is a technical step. And so you just need to parse this sentence and convince yourself that it's true, but it's just a technical fact, okay? We don't care about that too much. I want to emphasize, A, that the positive definite is going to be crucial in showing that this is a good inner product, okay? That's where we need it. We haven't used it so far. It's going to enter here. And then we just stop and realize that we actually achieved what we wanted. Given a positive definite kernel, up to these two steps that I skipped, we are now building a space of functions. How do they look like? They are linear combination of kernels at points. And the point that, in some sense, you allow yourself to consider any sequence of any arbitrary length, even infinitely many things. There is no training set. There is no data here, okay? It's just a construction where the functions that are inside, you can just view them now as linear combination of kernels. And notice that this is a new fact. We didn't have it before. We have the frequency point of view. We had the inner product point of view. Now we have the fact that these guys can be seen as linear combination of kernels. So for example, if you now take Gaussians, which again is one example that you can prove to be a positive definite function, you're taking linear combination of Gaussians, where centered at some point. Okay, this again, it would be an example. You basically say, in one dimension, I take Gaussians of a prescribed shape, and then I put Gaussians on these points. The width is fixed. Okay, how large are these Gaussians is fixed once and for all by this gamma. Whether they are mountains or valleys and how tall they are is actually given by the choice of these guys. How many Gaussians? As many as I want. Centered where? As many as I want. The weight, okay? But you can now still understand, that you could do, for example, stuff like this. And basically, taking that linear combination will be connecting the tips or bottoms of these mountains. So you can imagine now that you have yet another way to build function by combining these kernel functions. Notice that but this can be anything, right? Come up with a positive definite function that you like on graphs or strings or whatever. There is your function space, okay? You build a linear structure, and you can think of your function essentially if they were vectors. Everything we're playing, you're going to see everything going to linear algebra. Okay? So again, this proof is not easy, but these are the main two steps that are constructed are interesting because basically they show A, that you're going to take linear combination of kernels, and B, that you use positive definites to build an inner product, and then some more technical stuff. No, because here, you see that here I allow myself to take linear combination of any length, and this is why I call it H0. The last step of the proof, the one I have to complete the space, is the space where I actually allow this M to go to infinity. Okay, so the H0 version is the version where I complete the space. So if you want, the right notation will be that H is going to be the completion of the space H0. Again, this, but you know, I tried in all ways to see if there is an intuitive way to convey this, but really, I don't have much more than basically say that space, this space essentially might have holes. You have to fill them in, and that's what you call H. You have to be sure that, again, you can take infinite, okay? But the good news is that now we have a much more, you know, look at the difference between that definition, one on evaluation function, and this guy here. Here I say I take a positive definite function and I build a space that looks like this. All right. Okay, so this is chapter 2 of this story. Let me give you an abstract of chapter 3, which will be feature maps. Before I do that, any questions on this? Plane is linearity. You can check. You can check that essentially you can. Again, so you're asking about how to check that it doesn't depend on a specific representation of this, and define. It's possible to check. This again is like I'm not proving to you. I'm just defining this way, and giving you the intuition that it's symmetric and positive definite, and this is enough to get some of the properties. You also need that it's a well-defined, unique inner product that doesn't depend on the specific representation. You can do that too, and we're just skipping that. I'm happy to discuss. Yes.
Always the positive becomes the reproducing kernel.
Yeah. Because I guess I didn't. So the thing right now, what I show you up to now, that this is a Hilbert space. Okay. You can check that by construction, always a reproducing kernel Hilbert space because the function kx belongs to the space by construction. And if you now do f of x, you can always write it as this. Again, let's do it for H0. You can check yourself on H0. Because the way I define inner product, the function k that I start from is the reproducing kernel of the space. Okay? So by construction, I build not only a Hilbert space, but a reproducing kernel Hilbert space. I start from a simple function, and I build the whole function space. Okay? Bunch. We're trying to reach the fact that right now, I gave you an example where I give you a space, okay? I define a space, and we just look inside of the space and check what we got. So for example, linear functions. Oh, I discovered that it is a reproducing Hilbert space. Function, the linear combination of atoms. I discovered it is a reproducing band limited function, Gaussian, blah, okay? Here, suppose you ask me, okay, but how do you build these spaces? How can I build one of these spaces? Here I'm telling you, well, if you give me a positive definite function, it's one way. Because look, there is an equivalence between these two, okay? Whenever you have one of these spaces, you have a positive definite function. But the interesting thing, you can go back, and this is the way you do it. So what we're trying to achieve is to realize that these spaces are intimately connected with positive definite functions. They're essentially equivalent to the existence of very special positive definite functions, okay? So talking about reproducing kernel Hilbert space, or talking about positive definite function, it's a matter of where you want to start. I started here, and I ended up here. I could have started here and going back there, okay? Because I just built a space of function with those properties.
The Hilbert space H0 is just something built up from the K you predict.
Yeah. So again, the game is I don't have A, I have K. I try to build H, and I want my H to satisfy all those crazy properties here. Absolutely, yes. And I get all these properties for free. Okay? Questions?
So exactly what additional properties do you get for free apart from what is already given? Like you already know it's positive definite. You don't need to build a.
You can go the other way around. So you're thinking about, I'm sitting in H, what do I get for free? Okay, and I'm telling you, you can go the other way around. I can give you a K, and you can build. So did you know it a minute ago? Suppose if I give you, so you again, you invent a function with this property. Is it obvious that you can build a space of functions? That's what you got. Okay. That's it. So we get the effect that a completely new way to think about this. Again, the definition, if you want, is a reproducing Hilbert space is a space defined by a positive definite kernel. We could take this as definition. We can just say, look, a reproducing Hilbert space is a space defined by a positive definite function this way, and then derive those as properties of this space. Okay? All right, so let's stop here, and chapter 3 is for another time.